Hi everyone, from RickTech. Continuing with the tutorials, we have today the reinforcement learning Actor-Critic. So the Actor-Critic, as you can see here, we have the same from the DQN and reward, actions, environment, the buffer, the replay buffer, a mini bash that example to send it to the network. Now we have two networks. Here we have the Actor network that it will take the action. Here we have the critique. We're gonna critique that particular action from taking data from the environment. So the Actor-Critic implementing algorithms combines the benefits of both the value-based method and the policy-based method. The benefit of Actor-Critic algorithm is that it combines both of them, right? Combine the value and the policy learning. The actor is responsible for the learning of the policy, which is mapping from stage to actions. It determines the best action to take in each stage. Then the critique evaluates that action chosen by the actor by estimating the value function or the action value function. This value function helps to guide the actor learning process. Also, it reduces the variance in the policy gradient. Like reinforcement learning can suffer for high variance, which make training unstable and slow. The critique helps to reduce the variance by providing a baseline against which the actor's performance is compared. This makes the grading estimates more stable. It improves sample efficiency, generally more sample efficient compared to pure policy-based method because they use the value function to make better use of the information from each sample. By evaluating the current policy with the critique and updating the policy accordingly, these methods can learn effectively from freer interactions with the environment. There are continuous actions spaces. Actor-Critic methods can naturally handle continuous action space, making them suitable for a wider range of problems compared to discrete actions methods like Q-learning. The actor can directly output actions rather than having to discretize continuous actions space, which is often required in value-based methods. On policy learning, so Actor-Critic is on policy learning. Many Actor-Critic like A3C, PPO are on policy, meaning they update the policy based on actions taken by the current policy. This is advantageous in environments where the dynamic change over time or where we need the policy to be stable and safe. Then we have scalability and parallelization. These methods can be effectively scaled and parallelized, for example, in asynchronous advantage Actor-Critic A3C. Multiple agents interact with the multiple instances of the environment in parallel, so they're learning from the environment, all of them from the same samples, which speed up the learning and help with exploration. So there will be more agents trying to explore the environment with different actions, and because it's in parallel, we can speed up the learning. So for practical considerations, we improve performance in complex environments. This method often performs better in complex environments, such as those with high dimensional states or action spaces, because they can leverage both policy and value function for more informed decision making. Also, its flexibility is good. It offers flexibility in terms of architecture and designs. For instance, the actor and critique can share network parameters or have separate networks. Various extensions and improvements like PPO, DDPG, and ASC build upon the basic Actor-Critic framework to handle different challenges and improve performance. So here we have equations for Actor-Critic. We have here the parameter that belong to the actor and the parameter that belong to the critique that need to be updated in the Actor-Critic design. We have the grading of the loss function here. So we have the policy here, policy, and the parameter, the policy theta of the actor. So we got the gradient of the objective functions. We have the reward, we have the discount factor, which determines the importance of future rewards. We have the value estimate of the next state, and we will have the value estimate of the current state. This term, reward plus discount factor multiplied by the value estimate of the next state minus the value estimate of the current state, is called the temporal difference error, which measures the difference between the predicted value and the observed reward plus the discount value of the next state. Now we go to the actor parameter. This describes the day rule for the actor parameter. Theta, alpha is the learning rate. This is the policy gradient calculated. The policy parameters are adjusted in the direction of the gradient to maximize the expected return. Then we move to the equation number 3. This equation defines the advantage function, which is the TD error as we mentioned previously. This part, reward plus alpha plus gamma, and the value function of the next state is called the target value. It represents the immediate reward plus the discount value of the next state, and phi is the value function estimated of the current state. Now for the last function, it represents the rule for the critique parameter. This is the learning rate, this is the gradient of the loss function with respect to the value function parameter phi. The critique is a day to minimize the loss, which is typically the mean square error between the predicted value and the target value. So how to implement Actor-Critic agent? We had the same attribute, the agents before as DQN. We had the state dimension, the action dimension, the gamma epsilon buffer, replay buffer to store the experience. We had the actor network and critique network. We have the method to build the model. Remember, choose actions learned at the target network. So the replay buffer, the purpose is to store past experience to break the correlation between consecutive experience and stabilize the training. So we don't want that the next data of the dataset or of the buffer have a lot of correlation between them. So we sample afterwards from that buffer. So we have init to initialize the buffer with the size we want. Then you had the add function to record the experience, and then we had the sample that randomly sample a batch experience. You can see here small algorithms or a small script just showing how to declare your replay buffer. For the Actor-Critic network, we have here also another picture of how it could look. In this case, we show a simple Actor-Critic with input, hidden, and output layer. So here we have hidden layers, and we use the ReLU activation to introduce nonlinearity, making the network capable of learning complex functions. The output layer uses softmax activation to produce a probability distribution over actions, which is suitable for policy gradient. Then we have the loss function. This is a categorical cross entropy, which is appropriate for training with probabilities and discrete actions space. So in this case, we are using discrete actions here. Dimensions, right? Could be 2, 3, 4. So that's why we use cross entropy. We use softmax activation because you know this actor is on policy, right? We need to find a policy, so we need a distribution. Then we have the critique network. It uses the same ReLU activation for the same reasons as the actor. Then we have the output layer. In this case, only a single neuron with linear activation to the output state value because we want the value of that state. Then we had the loss function, mean square error, appropriate for regression tasks such as estimating a value function. Here again, the design. So what is the reason of ReLU activation in hidden layers? ReLU rectified linear unit introduces nonlinearity into the network, enabling it to learn complex patterns and representation from the input data, avoiding vanishing gradient. It helps mitigate the vanishing gradient problem that can occur with other activation functions like Simon or tangent. Especially in deep networks, these allow for more efficient and faster training. Simplicity and efficiency. ReLU is computationally efficient because it involves simple operation thresholding at zero. This made the training process faster. Here just the line code with the hidden and the activation function. The soft mass activation in the output layer, probability distribution, right? It converts the raw output score from the network into a probability distribution over the possible actions. Each output value represents the probability of selecting a particular action. Policy gradient. In the context of policy gradient methods, having a probability distribution over actions is essential for sampling action and computing the policy gradient. So why categorical cross-entropy loss? It's suitable for classification and it maximizes log likelihood. So for classification, which is essential what the actor is performing, it compares the predicted probability distribution with the true action distribution. Maximizing log likelihood encourages the model to maximize the log likelihood of the correct actions. This aligns with the objective of policy gradient method, which aim to increase the probability of actions that lead to higher rewards. Benefits of AIDEN optimizers. So here from the DQN, we could say the same advantage of using AIDEN optimizer for Actor-Critic. It adjusts the learning rate for each parameter individually, which is beneficial reinforcement learning where the importance of different features can vary over time. This is especially useful in environments, for example, with forced state and actions, where certain actions might become more relevant as the agent learns. Efficiency. AIDEN is computationally efficient and has low memory requirements. This efficiency is crucial when dealing with a high-dimensional action space, like 8 actions, ensuring faster convergence. Handling noisy gradients. This often involves noisy gradient due to the stochastic nature of the environment. AIDEN mechanism of combining the advantages of both RMS Pro and SGD with momentum help stabilize the learning process in such noisy environments. The mechanism, moment estimation, and calculate adaptive learning rate for each parameter by keeping an exponential decaying average of past gradient and past square gradients. Bias corrections. So why we have this mean square error loss? The same goes for the DQN, suitable for regression, stable gradient, error sensitivity, and the mechanism use loss calculation as the average of the square difference between predicted Q value and the target value. This encourages the model to make predictions that are as close as possible to the target value. Gradient descent process adjusts the model parameter to minimize the square error, ensuring that the predicted Q value converge towards the target Q value over time. In summary, implementing an Actor-Critic algorithm is beneficial because it combines the strength of both policy-based and value-based methods, leading to reduced variance in policy grading, improved sample efficiency, and better performance in complex and continuous actions spaces. The integration of the critic's value function with the actor policy functions allow for more stable and effective learning, making actor critique method a powerful tool in the reinforcement learning.